When working in C programs, you're often working at the bit level. And in this video, we're going to take a look at how can we specify bit patterns using bit literals or hexadecimal literals. And we're also going to take a quick look at the different widths of blocks of memory we can use to store our objects and the implications of using unsigned binary values versus signed binary values when thinking about integers, right? So unsigned and signed integers and the ramifications of choosing either in our C programs. We'll look at some standard new types that give us a lot of control over the size of the integer variables we're working with. And we've got a little mystery for you to resolve in a piece of code that has some surprising results in C. In the next video, we'll look at bitwise operators, which allow us to operate at the bit level. But for now, let's look at how do we actually specify literals at the bit level and think about sizes of our integer variables in memory. So this is the mystery. This first slide here is a mystery that I'd like you to think through. And the question is, without running this code, what do you think the output is? It looks pretty innocuous, right? We've just got two unsigned integers, a and b. A is 1, b is 2. Since neither of those are negative, that's fine. We're doing something interesting on the next line. We're subtracting b from a, right? And we're printing out the decimal, the decimal interpretation of that. The d will print out an integer. That's the sign in the printf. The printf symbol %d will give you an integer there, and it's going to be filled in by the second argument here, whatever that computes to. Right? So then the question is, well, what about the lines of code below it? What do we expect the comparison of that subtraction to 0 to result in? And which of these branches of this if-else statement will be evaluated given this code? I want you to pause the video here, think about it, and we'll come back to this at the end because there's some surprising results happening here that will make sense after we get through today's subjects. But I can almost assure you that no matter how consistent you try to be in your thinking here, there's something surprising about the way this works. So we'll come back to it. So how do we represent bit literals in C? Well, we can use what's called a binary literal, and that is a 0 followed by lowercase b and then your bit pattern after that. And there's an example of this here. I would encourage you to go ahead and open up in your container a new C file. You can call it, maybe make a directory for it. We're working on lesson 14 here and reproducing this little C program, right? And notice we are saying, and there's an unsigned character, and remember a character variable or the character type in C always corresponds to 1 byte, so we can store 8 bits, and here we've specified those 8 bits. And the way we're specifying those bits is 0 followed by a lowercase b, and then the bit pattern as numbers that we can type in. The b here is case insensitive. It could be uppercase, it could be lowercase. Typically you'll see when people are doing this, they will use the lowercase b. And this variable name was just a coincidence that it was b for binary. We'll use an h for hexadecimal later, but we could have named this variable just like any other variable using whatever name we'd like. When we compile this and run it, we'll see that it results in a value of 230. So let me go back to my terminal, and I've gone ahead and set up a file named bitfields.c. And if I open that in Vim, you'll notice that this is reproduced from the slide. And if you want to get to this point, pause it and come back once you've got this code in a file. That'd be great. Go ahead and do so. So let's try running this file and compiling it and running it, right? So we can't run a C file directly. We must compile it to machine code first. So GCC, and we're going to enable our warnings. So all warnings and extra warnings, and the D for debugging symbols, and the standard we'll use is C11, and we're going to use bitfields.c, right? And I can tab complete that because it's a file in my current directory. And after that completes, if it's successful, if that command exits with a success status code, then we will try running a.out, which is the compiled program. Right? So that and says if the previous command exited successfully with an exit code status of 0, then we will do this. Otherwise, if it didn't exit successfully, we expect to see some errors as part of its output, and we're not going to attempt to run a.out. So we run that in 230. Awesome. So this is an unsigned character. What if we did a signed character? Right? So if we go back in, and I want to jump to unsigned. So I'm going to use my teleportation and do a / and uns is enough. So / uns, enter, boom, I'm here. And now I want to delete these two characters. One of the keys that we haven't discussed yet, but is useful to introduce to you now in Vim that deletes one character at a time but leaves you in normal mode is the X key. So X will delete one character and leave you in normal mode. And when you just want to knock out X out a few characters, that's a handy thing to know, right? So I've just changed this to a signed character. And by doing so, we're going to interpret this bit pattern as a 2's complement pattern, which means that this high order bit is going to be a negative value. So we actually expect the ramifications of this when we go and we interpret this as an integer to be a negative value, right? So let's convince ourselves that that's true. I'm going to save my work in Vim, exit back out, and then try recompiling and rerunning my program. And sure enough, look, when we interpreted that same bit pattern, right? We didn't change anything about those bits, but because we interpreted it as a 2's complement signed integer, its value is -26 here. Cool. You can also use hexadecimal literals in C. In these, you begin with a 0 followed by an X, and then the hexadecimal patterns. It's once again case insensitive. You can use lowercase or uppercase. I would encourage using a lowercase x and uppercase hex digits just because they're a little bit easier to read, and that's pretty common, but it doesn't actually matter because the numbers are what correspond, the digits A through F, whether they're uppercase or lowercase in hexadecimal, they correspond to the same values, right? You've probably seen hexadecimal values in HTML and CSS if you've used color codes in HTML. And our git commit IDs are also hexadecimals, right? So there's many places where hexadecimal comes up. And when we're specifying bit patterns, it's actually more common that programmers will choose hexadecimal because it's shorter. Each hex digit represents a nibble or 4 bits. Right, so let's go prove to ourselves that this is the case and add these 2 lines below the lines in the file we were just working in. And I want to point out that you've translated or interpreted this representation, OXE6, or E6, the hexadecimal value, to the value 230 if you wanted to treat it as a decimal integer. Okay, so I'm going to open up my file again. And I want to go to line 6, right? Because I want to enter some new lines after that. So I'm going to teleport there with 6 as my line, and then capital G, and boom, I'm there. And then if I want to insert a new line of code below where I am, I'm going to press the O key, and boom, I'm on a new line. I might set up an extra line of white space here. And let's do an unsigned character and H, and OXE6 was what the slide was doing. And then we're going to run the same line as above. Actually, just to get some practice with Vim, I'm going to go back to normal mode. And I'm going to go back to line 6. So 6G. And we can do our line level operation of yanking, right? So I can YY, and then I can go to 9. So 9G for line 9. And I can paste it, right? And now I can move forward with the F key to the B character, right? And if I wanted to replace just this word, I can change the word, right? So CW will change that word B. And now I can say, okay, the actual value that I wanted to give here is the H character. And as soon as I do that, the previous warning on the line above that, hey, you set up a variable that never got used went away, okay? So now we've got our code here, and let's try running it. Right? So I'm gonna capital ZZ to save and quit, recompile. And this time around, because we treated that hex pair of hex digits as an unsigned value, we get a positive value out of it. And if I were to go, once again, / to teleport using a regex search to and then I can use XX again to delete those. And then I can save with ZZ to change that value to an unsigned. We can see that that same bit pattern, which we specified in binary before, can be specified with hexadecimal on the second set of lines, means the same thing, has the underlying same bit representation. And here, when we interpret that using a signed 2's complement system, we get -26. All right. So those are two ways that we can represent bit patterns in C directly: hex literals and binary literals. These actually wind up being in many other programming languages too. Python, I believe Java has the same, and you'll see these in many places as well. It's just more common that you would see them in C programs because we're working in a systems language. Next, I want to talk a little bit about some of the common types and sizes in memory. And in the book that you're reading, the C programming language, the standard types were things like char, int, unsigned, long, and over the years, depending on the architecture of the machine and the compiler you're using, you weren't necessarily guaranteed how many bytes of memory each of the types that you see in this left-hand column were going to result in. And so depending on your system, you might get different sized areas in memory reserved. Well, in the 90s, people realized, hey, we'd really like some strong guarantees on how many bytes of memory an integer type has associated with it and whether it's signed or unsigned. And so people, so the standards committee set up a standard file that's a part of every C distribution now. That's the standard integer header file that includes the definitions for the different widths of integers, signed and unsigned, that we can use. And so notice there's a common pattern here, uint8_t. And _t, when you see that in C, often denotes that, hey, this is a user-defined type that's not built into the C. This isn't built into the C programming language at the core, but the standard integer header file is defining these types and specifying their meaning exactly to say 8 refers to the number of bits that this integer is going to have allocated for it when we use a variable of this size in memory. And the U is short for unsigned, right? So that's going to give us only positive values and a range where 0 is going to be the lowest, and because there's 256 different values, 255 would be the highest value. Notice when we use a signed character, or what we should start doing moving forward, we'll be using the standard integer types. If we use just an int8_t, that's a signed integer that's 1 byte or 8 bits. And because it's 2's complement, we've got that sort of off by 1 issue where our negative range is slightly 1 higher than our positive range. So we can represent between -128, 127. Positive. Same idea when we get all the way down to the larger integer sizes, such as a 64-bit integer. And here, notice this is going to be an integer value that takes up 8 bytes of memory, and we can represent some very, very large numbers, right? So I don't even want to try and pronounce these numbers. I don't think I could, but you get the sense that the same trade-off is occurring, right? With an unsigned large 64-bit integer, you can represent a giant positive number, and then as soon as we go to a signed 2's complement 64-bit number, we're splitting the difference, but the negative side gets 1 more, right? And at that level, it's certainly a wash. So it's best practice in today's C programs, and we're moving forward going to encourage anytime you're working with integer data or specifically with binary data to use these standard types that have been defined in standard int.h. So we'll need to start including that file, and then we can define variables in function signatures, both parameters and return types, that use these standard integer widths. I want to talk briefly about data in memory. And so data in memory is arranged in a really interesting way. We've got this problem where we want to be able to work at the byte level, right? We need to be able to address individual bytes in our programs. But some of these types are made up of many bytes, right? Like a uint32 has 4 bytes in it. A uint64 has 8 bytes in it. And so if you can imagine, we declare 2 uint32 variables in memory. And I'm just sort of going to wave my hands here and say that this is the memory that's going to correspond to a frame, a functions frame on our call stack, such that the bottom of the frame might be at address 0 in this relative range of addresses, and the top at F, right? But this is just somewhere in memory. We're not going to write out the full address, and we're waving our hands here. There's this interesting question of, well, how do I arrange those bytes given my bit field, right? And do I want the lowest significant bit to be in the first range of bytes, in the highest address of bits? So here, notice we're making the decision to store the low order bits. So here with B, its value is 2, so it's got a 1 in the 2's position. And so this is the lowest order of the whole range, which makes up these 4 bytes here. And we're storing it in the lowest value in memory, right? So 4 is going to be the address, or I should say the lowest address in memory. So we're storing that low order bit field of the sequence of 4 that make up this entire uint32 in the low address, right? So the high order bits in this format would be if we had a very large unsigned integer and wanted to have a 1 in its most significant digit, we would put the most significant digits in the highest address in memory and the lowest significant digits in the lowest address. And same with A, we're seeing that that's happening here. It turns out you could imagine a world where this is opposite, where we put the highest order of bits in the lowest address in memory. And this winds up being a system, an architectural design consideration. In our modern Intel chips, this is the format shown on this slide, which is called little endian, meaning our little low order bits are stored on the lowest addresses in memory, is what's chosen. And this is how our memory is arranged when we start thinking about, well, how do we actually order the blocks of bytes in our computer's memory? And for right now, we don't really have a reason for worrying about this, but this will have interesting implications because other systems have chosen what's called big endian, which make the opposite decision and say, let's store the highest order values in the lower addresses and the lowest order in the highest. Ultimately, I think the intuition for this, we're going to come back to when we think a little bit more about how a program's call stack grows and how we think about where we're storing most of our variables that are dynamically allocated for us as we call our functions and things like that. So we'll come back to the details of this in more depth later, but I think this little endian scheme tends to make more sense when we think about storing our data in stack frames that work from the top of the stack down and grow in a downwards direction. And that's in fact how they work in a modern Linux and Windows systems. We'll come back to memory layout in a future lecture. So let's resolve this mystery of the opening question. And I've actually gone ahead and written this program out. So if I look at mystery.c, we can see that this is exactly what was shown before. We've got these 2 variables, A and B, and both are declared to be unsigned at the top. So let's try compiling it and see if we can explain what's going on. So WALL, WExtra, debugging symbols, and standard C11, and mystery.c is the file, and we'll go ahead and run the program. Something really interesting is happening here. Notice that our first printed value is -1. All right, so I'm actually going to write this down relative to where we're seeing it on the slides. All right, so this is -1. This results in a value of -1 being printed, even though these are 2 unsigned integers. So we've got a little bit of a head scratcher there. Right? But if that's -1, then we would expect, well, okay, -1 greater than 0, that's false. -1 equal to 0, that's false. -1, and then our else would be the only thing. So we would expect A less than B to be printed here, right? But is that actually what was printed? So let's go back to the output. What was printed was A is greater than B. So somehow, in this line of code, we see -1, which feels about right. I mean, when we're thinking about this and we ignore the fact that this was supposed to be an unsigned integer, so we shouldn't be able to represent a negative value with it. well, it turns out it's going to come back to some interesting implications of this %d symbol here. But let's go back to what actually wound up getting printed, which was this line, right? So this line of code got printed, which means that a minus b, when we evaluated it in this position, was some number greater than 0. Okay? Let's try and unravel this by thinking through what's going on step by step. So if we think about our bit field representations of a, this is an integer by default, and I should have chosen here one of our standard types, but here we had the initial mystery revealed before we talked about our types, so I didn't use the standard type here. I'm just reproducing the first slide of our slide deck. But this is a place where we should have used a uint32 type instead of unsigned int here. But on a 64-bit machine, typically this will resolve to a 4-byte value or 32-bit value. And so when we look at the unsigned representation of these two numbers, we have the bit patterns that you see on the screen. When we subtract, we typically are going to recast our numbers to be what they would be negative, right? And then we add them together. And this is true for both unsigned and signed through some clever tricks in hardware. Right? So when we recast b to be the negative version of it using 2's complement, notice the point was you flip every bit and then you add 1. So if we flipped every bit, we would have had 1, 0, and then all 1s. But when we added 1, we would have had to shift and move over 1 in that into the 2's column and reset our 1's value back to 0. And so now when we take negative b and add it to a, what happens is we are going to have a field of all 1s. Well, what's interesting about printf is the D format here is assuming that what you're giving it is going to be a signed integer that has 2's complement representation. And so when you represent an all 1s, no matter what the 2's complement bit field size is, always is a value of -1, right? So this is always going to be -1 no matter how many bits we have, as long as we're using a 2's complement scheme. So at this point, because we said, hey, print a signed interpretation of this and use 2's complement in the process, we see -1 printed, right? And if we had used the U key symbol here for unsigned, we would have seen a very large, because this would have been a positive number, and we can think about this would have been a very large number, the maximum positive number from a 32-bit integer, which if we went back to our previous screen is a 2 billion sum, and then that would have been what it printed, right? Next, what happens is when we make a comparison in C, it's going to choose the left hand of the greater than operator's type. In this case, that's an unsigned integer for making the comparison, right? So when we do this subtraction and we look at the same bit field, we're going to treat it as an unsigned integer. And that unsigned integer is greater than 0. Right? So all 1s, when we think about it in an unsigned sense, is going to be greater than 0. If this were a signed integer, we would have to interpret this in the opposite way using 2's complement, and this wouldn't have been true. Right? So when we do a comparison, there's these funky rules in C which say the left-hand side of the greater than operator is going to be the type that's chosen to interpret our bit field here. All right? And so that's why we get that result in our output. So this was a brief preview of, that problem will be in the practice afterwards. This is a brief preview of bit patterns in C and some of the literals you have available to work with them.